This is my last little broadcast before getting together with some collaborators to try to deepen our understanding of cohomology of symmetric groups, and in particular, attack the question of their what their structure, both additive and ring structure, are with integer coefficients. And so I wanted to bring some of the stories that I've been telling you recently together. There's on one hand this Fox-Neuwirth geometry, on the other hand this Hopf ring structure and divided powers structure, and they actually quote unquote play together pretty nicely. So, you know, the cohomology of symmetric groups, when you take the direct sum, which is up to completion, the cohomology of just the disjoint union, you get this free divided Hopf ring, and the generators just correspond to sort of submanifolds, if you will, almost folds of the configuration spaces where you've got 2 to the I points sharing I coordinates. And so what is the geometry of this Hopf ring structure? Just in general terms, and sort of first geometry, well, let's recall that the cup product is always going to be intersection, or more generally, pullback. In the paper with Greg and Annabal, we call it the pullback product of the geometric cochains. And then the coproduct is the natural map associated to BSN cross BSM to BSN plus M. And what I want to do to understand that, and we'll get back to the cup product in a second, because it ends up being much more subtle, and there's some things to clarify and correct. The coproduct is that natural map. And so what we're going to do is, again, I prefer, there's a couple models for this map. In this case, we're going to take configurations of endpoints in R infinity, mod Sn, I'll just say conf n and conf m for short. And I'm going to make a configuration of n plus m points by, well, if I've got these unordered points in R infinity and some more unordered points in R infinity, then I can just stack them together. And in this case, I would have 5 points. So I start with 2 and 3 points. I take their union, it's 5 points. Of course, there's some implied homeomorphism here, standard kind of thing, dating back at least to loop sum. And so then if you think about it, what is this map on Fox-Neuwirth cells? So again, let's recall that Fox-Neuwirth cells, Fox-Neuwirth geometric cochains. And what these are we set, we have these, if I'm doing configurations of endpoints, I've got n-1 numbers, and we use the dictionary order, and this is basically the closure. Well, this says that xi and xi plus 1 share at least ai points. With AI coordinates, not points, AI coordinates with the AI plus first coordinate of xi less than or equal to that of xi plus 1. Okay, so we've got these, you know, so pictures like this. Well, if this is our configuration space, we could have 3 points which share 1 coordinate, and then 2 points which share 2 coordinates, and that would be 1, 1, 1, 0, 2 as a Fox-Neuwirth index. So just such sequences of integers. And so if you then think about the natural map here, I claim that, so the natural map, of course, for geometric cochains is always, is also pullback. And really what we should say, instead of pullback, let me be consistent with a choice of notation and call this fiber product. The fiber product is what I mean sort of over the base manifold. Whereas here, if I've got a map between manifolds, this configurations of n plus n points is a manifold, as is the product of configurations of n configurations of m. If I've got a map between manifolds, then it really will be the natural map is going to be always pullback. If you have a geometric cochains, if you have geometric cochains, you can just pull them back if you're transverse. Maybe I should say that. So we want transverse pullback of geometric cochains. Well, the claim is that this is the way this works then is, well, I can never have any, the n and n plus first point can't, in this map from configurations of endpoints to cross configurations of endpoints, the n plus first point, the nth point can't share its first coordinate with the n plus first point. So what happens is, I'll just say it as a claim, and those of you who want to talk to me, either we have something scheduled or anybody watching this can reach out, is that A1, AN minus 1, AN plus 1 to AN plus M, this tuple is going to go, and let me call this map, by the way, really we should call this somehow mu mn, but then mu mn upper star is often, we call it delta mn because it's the coproduct. Doesn't have anything to do with the diagonal map though. This is going to be the following, either this, you've got these conditions split up if AN is 0, because again, that's a condition. If AN isn't, I think in terms of the converse, contrapositive or something like that, if AN is not 0, then such a cochain can't be in the image of mu mn. If AN is 0, then yeah, then of course you can have the configurations, the gammas over the configurations of m and n points, which correspond to this. So, this is going to go to 0. if AN is not 0. So coproduct has this lovely additive description, cochain level description. What about the transfer product? Well, here I want to switch the model for the map. So we're going to now let this mu mn map so what I start with again is maybe configurations of n cross configurations of m points. And that admits a map from something I'll call configurations of n comma m points. So these are the configuration of points in R infinity where n are, say, labeled red and m are labeled blue. And then if I just forget the blue ones, I've got the endpoints, which are labeled red. That's the first projection map. Or forget the red points, I've got the blue ones left. That's the second. Take the product of those maps. So this is an equivalence. And then here we have the covering map, where we just forget the labels. So this is a covering map. And so, so we're going to actually trace through. We're going to have, you know, say some two different Fox-Neuwirth cochains over the product of the configuration spaces. We're going to think about how that pulls back to the configurations of red and blue points together, and then we're going to and then we here we have our usual sort of Fox-Neuwirth tensor Fox-Neuwirth cochains. And here, of course, we have our Fox-Neuwirth cochains. But in the middle, these are going to be Fox-Neuwirth with sort of colors. So I have my A1, AN plus M, but I also have a sequence of colors that starts, I guess, to the left, but continues. So maybe the first point is red, the second point is blue, the third point is blue, and maybe red again. And then maybe my last point is blue. So we have some additional data because we've got these two colors. So what I want to do is describe the natural map for the first product of projections, and then this for getting labels, this is going to be also for getting labels. So the map here forgets labels. Right. And so then what happens here, and here's where I claim we're going to get some shuffles. So let me do an example. So it suffices, we want to do this composite. So we want to understand, I'll put it in green, this natural map. Because the transfer is just going to forget labels. So we have our Fox-Neuwirth cochain, the tensor product of Fox-Neuwirth cochains, in other words, a Fox-Neuwirth cochain over each configuration space. We want to understand its transfer product into n plus n points. And so it's the second map is for getting labels. It suffices to consider the first map. Let's give a simple example of trying to calculate that natural map for that for the map, that product map that's an equivalence. So let's just think about these Fox-Neuwirth cochains. So this tells me that my two red points share a coordinate. And this second thing tells me two blue points share a coordinate. So really they're sort of lying on some plane here. And what I want to do is think about how that pulls back to if I've got collections of red and blue in R infinity. And by the way, you might wonder why this thing is an equivalence. Here we really use, this is in R, let me, I've been omitting it, the configurations of endpoints in R infinity, mod Sn. Here we're using R infinity. So for example, a very basic fact is configurations of endpoints in R infinity is contractible. And so is a model for ESN. So the blue and red points, they are like, once I've colored them, I might as well sort of take the blues and take the reds, and you can play these games with coordinates and have them say in on typical points of S infinity, but in S infinity is contractible. So then you really just have those configurations. So that's one informal way to say why this should be an equivalence. I'm sure there's plenty of others. So anyways, the question is, what are if I'm going to take the pullback of those geometric cochains, I need to know what here, pullback means what here maps to these. Well, you can immediately come up with a couple of pictures. I could have, not surprisingly, my red points that share a coordinate and my blue points that share a coordinate, and that would project down. Or I could also have my blue points come first, and then my red points after them. And what you generally see is, and then especially, let me do one other example. And then I think and then I'll state. So what if I have 1, 0, 1? So that means my blue points come in 2 sets of 2. Or I guess my red points is how I was using them. So my red points come in 2 sets of 2. Yeah, maybe I'll even make these 2. So my first 2 red points are on some plane like this. My second 2 red points are stacked right on top of each other. And then you can wonder which kind of configurations project onto those. Again, my blue points were just 2 that shared first coordinate. And the answer, and when I say or above, that's really plus. So my, there's going to be 3 terms because I will project onto the same kind of picture regardless of how the blue is quote unquote shuffled in to the red. So I could either sort of have all the red first and then the blue follows, or the blue could come in between. The red is sort of split by the blue. or the blue could come first. And those all would project onto the same pair of configurations. So I don't know, at least up to, yeah, I mean, when I take all such. There might be a union here or some that I'm eliding, but this is the idea. And in general, what you do is you shuffle the blocks. So if my A's have these sort of these different blocks, and my B's have these different blocks. Then under this transfer product, I'm going to get the sum of sort of the shuffles of the blocks, and I'm going to take one of the A or B blocks. I have to start with either the first A block or the first B block. Then I could switch to the first A block, maybe even do the second A block. Maybe switch back to the B blocks, etc. So that's the geometry of the transfer product. It really just says, though, that's a formula. The geometry of the transfer product more informally just says I've got some condition on endpoints. If I'm really thinking of these Fox-Neuwirth things as submanifolds, they aren't quite on the boundary. Their interiors are embedded. So I've got some closure of a condition on my endpoints and closure of a condition on my endpoints. And again, the key map is this covering map, and it says, well, can I take n plus endpoints here? Oh, I guess I just, this forget labels covering map. Take n plus endpoints, take my conditions here, and kind of lift them. What happens if I take my n plus n points and I color them all possible ways? N of them are red, m of them are blue. What conditions do I get on those points? And under this model, where we've got the projections on the configuration spaces, and then followed by that covering map, what you end up with is just sort of shuffles of conditions. At the very minimum, if each has one block, and the first example we did was like this, then you have, right. So notice here, this is an important point. I said or, let me actually change this to a plus, because in the cochain world, then when I forget labels, I'm going to get 1, 0, 1 plus 1, 0, 1, which, because we're working mod 2, is 0. So this says the transfer product of two, in this case, gamma 1s, is 0. And that's a rule because it is twice something. And so we see this twice something again in shuffles. So whereas, let me do another example on the side. but 1 transfer 2 is going to be 1, 0, 2 plus 2, 0, 1. And I claim that that's going to be reflecting that gamma 1 transfer gamma 1 squared is, well, gamma 1 squared. But, right. I promised something about the divided powers in this language. So again, geometrically, so what is the geometry of all these in the informal geometry? Delta is again kind of split along. Split if the condition on n plus m points involves has no bearing, no zero as an amount of agreement on n and n plus first point. So it's really kind of split the condition when it is splittable. This is again intersection. I mean, for example, for BS2, so 2 points intersection with points which share a coordinate. Well, that's going to be not transverse. So you start to have to do things like 2 points which share their first coordinate intersect 2 points which share their second coordinate. That would be 2 points which share their first 2 coordinates. But notice that we're out of the world of Fox-Neuwirth cochains as we've defined them. And I should say that there's both some, we'll discuss further, errors to correct, errors whose thankfully whose proofs were just sketched. So I think and then you know, questions to answer then about how this goes. And the transfer product is you make a condition on n plus m points by imposing conditions on n and m points over all bicolorings. Okay, so you know, the gamma 1 transfer gamma 1 squared says 2 points sharing 1 coordinate, transfer 2 points sharing 2 coordinates. Means you've got 4 points. First 2 points share a coordinate, or actually not the first or last 2. 4 points, 2 of which share 1 coordinate and 2 of which share 2 coordinates. And then finally, the divided power operation is repeat a condition. So let's recall that 1 transfer 1 is 2, 1, 0, 1, if you will. So 1 divided power 2 is this key class 1, 0, 1. And again, the main conjecture I have, at least at the prime 2, is, I'll state it just at the prime 2, all 2 to the k torsion corresponds exactly to the 2 to the k minus first divided power. So all 4 torsions are the twofold divided powers in BS4. You don't have any 8 torsion, and you know, you have some more 4 torsion in BS6 because you can just take a transfer product with a unit class. But then there starts to be some 8 torsion in BS8, and the smallest degree family. This is the first 2 torsion. It's in BS2. This is the first. Integrally, I better do this, because otherwise you're not going to have an integer cocycle. So this is gamma 1 squared. This is gamma 1 divided power 2 squared, gamma 1 divided power 4 squared. And I claim these are the first torsion classes, lowest degree ones. And this family continues, but more generally, in the skyline point of view, there's going to be some deeper torsion when these columns get repeated because of this divided powers structure. Yeah, let me say a little bit more about the cut product, and I'll probably say even more in a further video or discussion. This does not play well with Fox-Neuwirth, despite the sort of conjecture with proof sketch that Chad and I made. The simplest example this is a cocycle. This is gamma 1, 2. And let's take the cut product with so this is what this represents gamma 1 transfer 1, 2. Okay, so that's all possible shuffles of a 1 with a 0 with another 0 around. And the way this is not going to equal to 2, 0, 1 plus 1, 0, 2 plus 1, 1, 1. I reordered things a bit. This would be, this times this should really just be gamma 1 squared transfer gamma 1. And that would correspond to this much. This is this new class gamma 2, and that has nothing to do with this cut product. Gamma 2 is indecomposable. What's going on is, of course, in order to, for example, get this 2, I have to take these 2 points share one coordinate, and here 2 points share their first coordinate. And I would actually have to make this on the second coordinate. And I could do that here and here. And then when I intersect 2 points share their first coordinate along with 2 points share their second coordinate, I'm going to get 2 points share their first 2 coordinates. But then this also needs to be the second coordinate. And so this 1 is a second coordinate kind of 1, and that ends up somehow actually co-bounding. So this is, I mean, first of all, when you play the second coordinate game, what is the ordering you're using, for example? But so once it means something, it's got to co-bound. So yeah. Fox-Neuwirth cells are wonderful ways to make some cochain level calculations with the coproduct and the transfer product, but not so much with the cut product. But that's a challenge, and there's some things to do maybe with generalizing, refining Fox-Neuwirth cochains for cut product calculations. Okay. yeah, that's, I think, what I'll do. I think the next thing, if I make another video, it likely would talk about some Steenrod and Bocksteins and go to some odd um, dimensional or odd primes, cohomology of symmetric groups with odd primes. But that will